Okay, this is an introduction to hypothesis testing, year one applied. This is a chapter with quite a high barrier to entry in terms of understanding. I really think that the first time people come across hypothesis testing, it feels very weird. It doesn't make that much sense. But with a bit of thought and a bit of context in particular, you can get your head around it. So I'm going to start off with a motivating example. So we're going to play a really silly game. This is a really silly game. Normally I would in class literally play it, but we're just going to do it as a thought experiment. So I tell you that what I have is a fair deck of cards. I'm not going to let you look at it, but it's in my hand. I've got a fair deck of cards. You can't see them. They're face down. I give them a good shuffle. And what I'm going to do is I'm going to come around the class and I'm going to let people choose, free choice, one of the cards. Now, if it's a fair pack card, I'm telling you it is. Half of them are black and half of them are red. So, if the randomly chosen card by the student is red, the class get a point. And if it's black, then I get a point. That's it. It's not a great game, but there we go. It is going to tell us something. So I go around, and the first student pulls out a black card. So I'm going to keep a tally. That's a point to me. Second student also pulls out a black card. That's a point to me. Third student pulls out a red card, which is good because I think maybe initially the class is always suspicious. They think there aren't any at all. The next couple both pick a black card as well, and I'm feeling pretty good about myself, and I'm definitely winning. Then a red card comes out. And then another one for me. Another one for me. And a red card. And we're up to 9. And another few for me. Then another red card. And then another couple for me. Oh, do my tally correctly. Another couple for me. And finally, the last card goes to me. So overall, the scores come out at 4 to 11. And so the question I'd ask to you is, do you think the game is fair? Do you think the cards are fair? Do you feel hard done by? The answer is probably yes. And this leads us to what hypothesis testing is about. Hypothesis testing is that enough evidence that actually for you to accuse me of cheating? Is it, statistically? Because that could have happened by chance with a pack of cards that was fair. Is that enough evidence to suggest that I was cheating? Let's do it another way. So I've got a coin and I flip it 20 times. I'm going to say how many heads and tails I get, and I want you to think, do you think the coin is fair? So say I flip the coins and I get 10 heads and 10 tails. Do you think it's fair? 9 heads, 11 tails, is it fair? 8 heads? 7? Do you think it's fair? 6? 6 to 14, do you think it's fair? 5? 4? Do you think it's fair now? 3? 3 to 17, do you think it's fair? 2 to 18, think it's a fair coin now? 1? What about if all of them came up tails? Do you think it's fair? Now, what I would think is that everyone thought that 10 was fair. Everyone thought that 0 to 20 was unfair and that the coin was biased. And some point in between, you would have changed from thinking it was a fair coin to not a fair coin. There's no doubt that you could get 9/11 if you just flipped a fair coin because chance says that could happen. That is a hypothesis test. You've just done one. Kind of. You haven't used actual statistical evidence behind it, but you've kind of done one because what you've said is there's a point at which you would accuse something of being unfair. So I think this is kind of what I'm talking about here. When I had some coins, I think you would probably come up with a judgment of this being unfair. I think you'd probably come up with this being a judgment of unfair, this being fair, and this being fair. Some point between here and here, you'd switch and change your mind. And that's going to be what we call the critical value. And we're going to find it statistically based on some agreed level of kind of caution as to how cautious we want to be with these things. And that is what a hypothesis test is going to be. We're not going to do a hypothesis test formally yet. First, we need to get some a bit of revision of chapter 6 on binomial distribution. It is really important that everyone has a really good go at this task. So what I really recommend you do now is pause the video, maybe take a screenshot, and have a go at really practicing these questions. The ones on the left should be able to do. The ones on the right are harder, but I want you to give it a really good go. So I'm going to pause for about 5 seconds, pause the video, have a go, and then I'm going to go through them. Okay, I'm back. Right, so I'm actually just going to show the answers to the left-hand ones. You should be able to get those. If you've made a mistake, think really carefully about what it means to be greater than and greater than or equal to, and go back to the previous chapter. For the ones on the right-hand side, they're going to take a little bit more thought, and you might have struggled with them. So again, I'm going to go through that now. So I'm just going to focus on questions 3 and 5. And you'll notice that I've actually got up on the left-hand side the cumulative binomial table. So this is cumulative. Now, you've probably been using your calculator up to this point. So I'm just going to show and remind again how to get that up on your calculator, because it is much easier on the calculator than using the formula book. And this is how you would do it. So you'd go to distribution, click down to binomial CD, go for list, and what you're going to want is to write the numbers 0 to 14. You could not write all of them in, but since we're doing n is 14, we're going to go 0 to 14. There. Then you're going to press equals, and you're going to type in your values that you need, 14 and 0.65. And you will get the table there. So if I just click down, if we say, you can see that we've got 0.8135, slightly different to the table to do with some rounding. If I actually click on it, you can see that it would round to 0.1836. We're going to be doing things mostly to 3 decimal places, so that will be sufficient on the screen. But you can see that this is the same as on the right-hand side. So you can do this all on a calculator at the same time. I will do this on the calculator at times in a minute, but for now I'm going to use my table that I've got copied out on the right-hand side. So this question says, find the largest value of k such that the probability of x is less than or equal to k is less than 5%. Before I use this, I'm actually going to bring up the binomial distribution, a picture of it. So this is using GeoGebra. You can't have this in the exam, so I want to reassure you that I'm going to do this completely without this, but we can look at this for now. So this is my distribution of 14, 0.65. It looks something like this, with the heights of each of the bars representing the probability. On the right-hand side, these are the actual probabilities of each individual value. So 0.051 is the probability of equal to 6, as in the actual probability of the height of 6, so that. So you note it's different to on the left-hand side over here, because that is a cumulative. This is the actual probabilities. but I can do cumulative at the bottom here. So if you look at the bottom of the screen now, I've got the probability of less than or equal to 6 is 0.0753, exactly matching what I've got on the table. So what I'm interested in is the probability of x, and I'm going to move this over here briefly so you can see it. Probability of x being less than or equal to k is less than 5%, and I want to find k. So k is the value along the bottom, because I'm going to say the probability of less than or equal to something is less than 5%. Well, the probability of less than or equal to 6 is equal to 0.0753. That's more than 5%. Probability of less than or equal to 7 is much bigger than 5%. Probability of less than or equal to 5 is about 2.4%. That is less than 5%. So that's more than 5%. The sum of all of those, the sum of these on the right-hand side, that's less than 5%. So 6 is too big. 5 is just right. 4 is okay too, but we could do better. We could get 5. 6 too big. 4 is not big enough. 5 is just right. It's kind of like Goldilocks and the Three Bears. It's just right. This is the best we can do and still be in the bottom 5%. So we know the answer is going to be 5. And if you got that, that's correct. But how could I see that on the table here? Well, I can see that because I can see that I switch over. This one is less than 5% here. This one is too small. And this one is too big. So the switch that I'm interested in happens between here and here. This is less than 5%, but this is not less than 5%. So what can I write down? I can write down the answer. The answer is going to be 5. So I might actually write that straight away. The answer is going to be 5, but my working is the probability of x is less than or equal to 5. That is equal to 0.0243, and that is less than 5%. The probability of x is less than or equal to 6, that is equal to 0.0753. And that is greater than 5%, so that's no good. So in a way, I'm saying that this is okay, and this is not good enough. And yeah, less than or equal to 4, that's also not that, like we could do better, and 5 is the answer, so the answer is 5. Okay, well, we could actually, in the previous slide, I noticed that there was also, I also set you the question 4, which was less than or equal to 10. Well, 10%. Well, actually, 6, 7 is too big at the bottom here. I'm looking at the bottom here. 7 is too big. 6 is just right. So if I go back to this screen, you can see the switch of 10% happens between here and here. Let me just write that to be really clear. Switch from greater than and less than 10% happens between here and here. Less than 10%, greater than 10%. So the answer is 6. So if I go back to here, the answer to this question we had is k is equal to 5. The answer to this question is k is equal to 6. They're very similar questions with a different value. Right, now let's have a go at this one. Now let's have a go at this one. You might want to pause now and have a go at this yourself based on what we were just saying, if you didn't get the explanation before. There's another, I'm going to give another chance to practice this too. So, probability of x is greater than or equal to k is less than 5%. Now, the real confusion here, the thing that finds people difficult, is that we've got two inequalities happening in the same question, and that's kind of hard. Remember, This is talking about where we are on here. So that is to do with that. And this is to do with where we are in here, because it's the percentages. So let's get rid of them. That's what I want you to be bearing in mind as we do this. So, what have we got? Well, the problem here that we have is that we want greater thans, and we've got less thans. The cumulative thing on the calculator and on here is all less thans, and we want greater than. So, let's have a look on here. I can switch this to greater than for us to give this idea. So I can switch this to greater than, and I want to know what is in the top 5%. What results greater than what is less than 5%? Well, I can see at the bottom that greater than or equal to 12 is about 8%. Greater than or equal to 13 is about 2%. So the answer is 12 is too big, 13 is just right. The answer is 12 is too big, 13 is just right. But we don't have greater than when we have in the calculator or on the table. So just remind that I could have this values on the calculator or in the table on the left-hand side. And I do recommend you use the calculator when you do this question. I'm going to do it on the calculator when I do this in the future. So, what we need to look for is if we're in the top 5%, we're over 95% on here. So the top 5% is going to be over 95%. Now in all of this, I want you to bear in mind that we know the answer is 13. 12 is not right, 13 is just right. So let's have a look over here. So where does it switch from less than to greater than 95%? Well, that appears to be here, which is surprising because we know the answer is 13. So it would have been nice if the answer was 12, but it doesn't quite work like that. And that's because we are dealing with less than or equal to here versus greater than or equal to. So the way I always do it is I look at this and I say that this is less than 95%. This is greater than 95%. And that switch happens from 11 to 12. On the calculator, I could see that that value here is less than 95%. That is greater than 95%, and that happens from 11 to 12. Ignore these numbers on the left-hand side. 11 to 12 happens here. So I write these values down. I write that, and I'm going to switch color, so I want to go to blue. The probability of x being x is less than or equal to 11 is equal to 0.9161. And that is less than 95%. The probability of x is less than or equal to 12 is equal to 0.9795. And that is greater than 95%. So that's the interesting switch, but how are we going to get that answer 13? Now bear with me, because this does take a little bit of thought. We need to change it into greater thans. And to do that, we need to do 1 minus. So I'm going to take this first one, and I'm going to do 1 minus. 1 minus the probability of x is less than or equal to 11 is equal to 1 minus 0.9161. And this is going to be 1 minus less than or equal to 11 is going to be the probability of x is greater than or equal to something else. Can you think what it is? Well, if you're not sure and you think you often make a mistake on this, I'm going to do a little box up here. I always draw a little number line. So I have got 9, 10, 11, 12, 13. And I draw a little box around the ones which I don't want or do want. So if I have less than or equal to 11, that is this. So that is 1 minus greater than or equal to 12. So that is going to be greater than or equal to 12. 1 minus less than or equal to 11 is greater than or equal to 12. And I can see that. 1 minus less than or equal to 11 is greater than or equal to 12. And this is equal to, don't ever make a mistake on these. Feel free to use your calculator. 9161 is equal to 0.0839. 0.0839, which is greater than 5%. So the other one, 1 minus the probability of x is less than or equal to 12, which is 1 minus 0.9795. That is equal to 1 minus 0.9795, 0.0205, and that is less than 5%. And so now we feel like we're a lot more back in the situation we had above. What is less than or equal to 12? Well, less than or equal to 12. Let's do that. Less than or equal to 12 is 1 minus greater than or equal to 13. So that is the probability of x is greater than or equal to 13. And that's where our 13 comes in. So now, just look at the first bit and the bit over here. Just look at the first bit and the bit over here. We have shown that greater than or equal to 12 is not okay, but greater than or equal to 13 is small enough. It is in that top region. Reminder on here, 13 is okay, less than 5%. 12 is too big. We get 0.839, which is what we got there. So the answer overall is that this is not okay, this is okay, and the probability of x, and the value of k that we want is k is equal to 13. And that is the answer that we want. Now, I started off talking about a card game. Actually, firstly, let's give the answer to the other one. So let's just go back a step. So the answer to this was k equal to 13. Have a go at this one. Maybe pause the video. Try this one now. And the answer to that, 10%. So we get 22% here. This is 8%, 22%, too big. 12 is just right. So the answer is k is equal to 12. Probability of x is greater than or equal to 12 is the answer. Okay, so what I was saying, we started off thinking about a silly game. Now we've started thinking about results that are in an extreme end of the binomial, i.e. the ones that are unlikely. Let's construct the binomial situation for the game that we played with the pack of cards. So, reminder, I said that there were 15 students. Probability of getting black and red is 0.5, so we're in this hypothesis test. We've got 15 is n, 0.5 is the probability. It looks like this. These are the probabilities of getting, by chance, if the pack is fair, each value of red cards. Now we got 4. We got 4 red cards and 11 black. So 4 red and 11 black. So we're down here. 4 and below has a probability of 0.05. So we can say that the probability of observing a result that was that weird or weirder is about 6%. It's about 6%. So it is very unlikely to see that if the pack is fair. If the pack is fair, we could see that. Of course, the pack might not be fair, but if it was fair, we could see that. The crucial thing is that it could happen. It's not impossible. It could happen about 6% of the time. 6 out of every 100 times we played that game, you would observe a result of 4 or less. So is it evidence for being unfair? Is it evidence to accuse me of cheating? Well, the answer is depends how sure you want to be that I was cheating. Quite often, we use a value of 5% to say that's sufficiently kind of weird enough. That's why we've been just doing it with 5% when we were working out those values. So I would say 3 and below, that's less than 5%. 4 and below, that's too big. That's not weird enough for us to say something is cheating. That's exactly the calculation that we just did. That's why it relates. So what you would work out is that 3 and below was the right value. Those are the values you'd accuse of cheating. It's called the critical value, would be 3. And any value greater than 4, you would say, that's not weird enough. I can't accuse you of cheating. So the conclusion is, this isn't weird enough. You can't accuse me of cheating. I might be, but you can't accuse me of cheating. I'm going to leave you in here because there's not really any questions on the exercise that I can do. I'm going to leave you with this. I want you to try and do exactly what I just did for the other, but for this new distribution. I want you to try for this distribution, the same question. And actually after that, you can make up your own. You can do other distributions and try and practice experimenting, calculating these questions.